So I have Chemistry 1010, Tutorial Sheet 1, 2024. We'll look at these interesting questions. So question 1, we're looking at the exact number. Question 2, we're looking at the significant figures, decimal places. I'll explain. So is question 3. Question 4, here we are trying to determine the number of atoms. So is question 5. Question 6, we are trying to find the mass percent of an element in glucose. Here we are looking at the law of conservation of mass. Here we're looking at finding relative atomic mass when you're given the isotopes atomic mass. And then look at question 9. We are determining the limiting reagent and predicting how much was yielded. Which of the following is an exact number? Without even wasting time. Exact means you're able to count. And of course, there are going to be cases where conversions may be involved, but we're not dealing with conversions. In a case where somebody would say 1 minute is equal to 60 seconds, that is also exact in terms of conversions. But where you've got something that you're able to count exactly, like 7 shares, no arguments, that's the most exact, or that's the exact number. We have question 2, when numbers are added, the limiting term is the one with dash number of. So what you need to understand for question 2 is addition and subtraction deals with decimal places. They are the ones that apply. So you always follow the one which is having the smallest or the least. So least or smallest mean the same, right? So smallest number of decimal places. Now when you're multiplying, which is usually the case in our calculations in chemistry, when you're multiplying and dividing, what do? You follow the least number of significant figures. It's the one that's going to restrict the result. What that means is, if you are going to divide 2.4 by, let's say 0.01, 0.01 has got one significant figure. So it means your final result should have only one significant figure. So the value with the least significant figures in multiplication and addition restricts or limits. Okay? And then for addition and subtraction, it's decimal places. So when numbers are added, the limiting term is the one with the least or the smallest number of decimal places. So B is the answer. 3. Give a number of significant figures in each of the measurements. So by now, you should be very conversant with the rules of significant figures. If you are not, all numbers are significant, except zeros. Zeros depends on where they are. Zeros in between numbers, for example, that zero is significant. Now, zeros that are used to indicate where the decimal point is are not significant. So these zeros, they are not significant. How about zeros that come at the end? Are they significant? So they are regarded not to be significant. They are only significant if we're going to put a point, let's say something like that. They become significant. Or if they come after, let's say 1.00, these zeros are significant. Okay? So I hope you've gotten that. So in terms of the question we're given, the A is having 1, 2, 3. Those are 3 significant figures. For B, ignore the zeros in front. So we have 1, 2, 3, and 4. These are 4 significant figures. We are now good to go to look at 4. We are now on question 4. Iron is the main component of steel, and that's the most important metal in industrial society. It is also essential in the body. How many iron atoms are in 95.8 grams of iron? So under stoichiometry, any question that's going to ask you to determine how many, implying you're trying to count, just remember Avogadro's constant. Alright? Avogadro's constant is what helps you to count. So the value is 6.022 times 10 to the power 23. Now, the units, I usually say the units for Avogadro's constant are per-mole. So it depends on what you're counting. In this case, what are we counting? We're counting atoms. Atoms of what? Iron atoms. So I can just say 6.022 times 10 to the power 23 atoms, or atoms per mole. So those are the number of atoms of ion or any element you're going to discuss. If the question was saying molecules, determine the number of molecules, where there's atoms would put molecules. And of course, there are videos where I've explained on how you can distinguish, but that usually occurs in cases where you've got oxygen and maybe just oxygen. If I'm going to ask you for determining the number of oxygen molecules, like in this case, what you're going to do is you realize that you just get the molar mass, determine the number of moles. In short, the formula will just become 6.02 times 10 to the power 23 molecules per mole. So the same value will work. You would have found the number of molecules if you are going to use the molar mass of that. Now, if you're going to find the number of atoms in a case where it's diatomic like that, it implies whatever value you're going to find multiplied by the subscript. I think that's very clear and important to take note of. Let's get back to our question. We've got our Avogadro's constant there. So I said the units of Avogadro's constant is just per mole. In this case, we are trying to determine the atoms, so it's atoms per mole. Now we multiply by the number of moles. The idea is the number of moles we're going to reduce on top are supposed to divide by the mole which is on the bottom. Now, with the information we're given, we are told we have 95.8 grams of what? Of iron. Now, iron, we can get its molar mass from the periodic table, right? So my periodic table is telling me the value is 55. So 55.845 grams. I've deliberately put it on the bottom so that I can cancel out the mass, and I know the units for molar mass is grams per mole, so the mole can be on top. So the grams can divide. This is a formula that some of you have mastered, and I don't like mastering it. Of course you can. Where you know the number of moles is the mass, which is the 95.8 divided by the molar mass 55. So grab your calculator and just divide that. So the number of moles I'm getting, if my calculations are alright, the number of moles I'm getting here, 1.71546 moles. So we can put that value there, 1.71546 moles. What do we do now to find the number of atoms? Of course, we multiply the moles, we cancel, and then what remains is now the number of atoms, right? So we can multiply 6.022 times 10 to the power 23. Now the value I'm getting is 1.033 times 10 to the power 24. The units remaining now are just atoms. So we've calculated the number of atoms. If we can go back to our question, in this case the only number we had was that. How many significant figures were they? 3 significant figures. So in our final answer we should have 1.03 times 10 to the power 24 atoms. So you've seen that whatever we've learned earlier is really now becoming useful as we proceed. Ammonium carbonate is a white solid that decomposes with warming. It has many uses, for example as a component in baking powder. It's also used in fire extinguishing. How many formula units are in 41.6 grams of ammonium carbonate? So I said whenever you see the word how many or you're counting, Avogadro's constant should come to mind. So irrespective of what the question is saying, look at ammonium carbonate. What is it? Ammonium is NH4. Carbonate it should be CO3, and then that's got like 2 minus. So if you come up with formula ammonium carbonate, you end up with something like NH4 with a subscript of 2 and then carbonate 3. I think that should be the way it should come out. So verify that from Google or any source that you have right now for the formula of ammonium carbonate. So if this is alright, we have to find now the relative molecular mass of ammonium carbonate. So we've got these 2. So 2 times the molar mass of our nitrogen. So nitrogen, if I check my periodic table, it's a value 14.01. and then 2 times the 4 there gives us 8 of the hydrogens. My periodic table tells me it's 1.009 grams per mole. And then carbon, my periodic table tells me it's 12.01. There's only one carbon, and then 3 times for our oxygen, which is 15.989 according to this periodic table anyway. So from there, approximately 2 times 14.01 plus 8 multiplied by 1.009 plus 12.01 plus 3 multiplied by 15.989. So 204.159. How is this? How is this? I think let me recalculate again. 2 times 14.01 plus 8 times 1.009 plus 12.01 plus 3 times 15.989. So the value was too big, yeah? So the value is 96.717 grams per mole. This is the molar mass. Now, you know, we're not interested in the molar mass. We're interested in finding the number of moles of this ammonium carbonate. So we can clearly just find that. So 41.6 grams divided by the molar mass 96.717, the units are grams per mole. So the mole will go on top. The idea there is you just divide the values, the grams will go, and then you remain with moles. Now you know that the number of moles that you're going to have is supposed to be multiplied by the Avogadro's constant, right? To power 23. The units are, in this case we're trying to find formula units, so you can call it that, formula units per mole. So a mole will end up dividing again, and then the ultimate units will be formula units, and then 41.6 divided by 96, that's giving us a number of moles 0.43 multiplied by 6.022 times 10 to the power 23. The value I'm getting is something like 2.59 times 10 to the power 23 formula units. This is to 3 significant figures in respect to the value we're given in the question. Question 6. In mammals, lactose, which is milk sugar, is metabolized to glucose, C6H12O6. The key nutrient for generating chemical potential energy. What is the mass percent of each element in glucose? So before we proceed, for any information, stoichiometry is a topic that I've taught from scratch, from the definition of stoichiometry to the most advanced complex, dealing with determining formula, titrations, everything, and there are a lot of practice questions on our site. So the link is in the description below. Don't miss out. You can access all the practice questions that you need to help you build confidence under stoichiometry, and this applies to all the chemistry topics, right? Organic chemistry, electrochemistry, thermochemistry, atomic structure, chemical bonding. You have access to them all at your own convenient time, and also PDF solutions to these questions are available on the site. Alright, so information in the description below. Let's continue. So here we're trying to determine the mass percent of each element in glucose. So you find the mass percent by looking at the molar mass of any element. So in this case, what the first element we're going to look at is carbon. The molar mass of carbon over the total molar mass, or which we are going to call the relative molecular mass of glucose itself, C6H12O6. Alright, so I'll guide you for the very first one, and then you can find for hydrogen and oxygen. So for carbon, The molar mass is what? 12.01 grams per mole. For a molar mass of the glucose, we can calculate it 6 times 12.01 for our carbon, and then for hydrogen 12 multiplied by 1.009 plus 6 times 15.998 for our oxygen. So approximately 6 times 12.01 plus 12 multiplied by 1.009 plus 6 times 15.998. So the value is approximately 180.156. So all the units, remember, are grams per mole, so they'll end up just cancelling out, right? So units don't matter in this case. 12.01 divided by that value times 100. So for hydrogen, sorry, for carbon, for carbon, in fact, it's not just the molar mass, it's also multiplied by coefficient. That's why it's messed up. So we have 6 of the carbon atoms. So 6 multiplied by 12.01. That's the total number of, that's the percentage that carbon is contributing to the molar mass. Now, determining its percentage, so that's giving us like 72.06 now over 180.156 times 100. So multiply by 100, so that's going to give us 39.9. That's 9.9986%. If we're going to round it off to reasonable number of significant figures, if you look at the values we've used, I would say the least number of significant figures we had were like 4. So if we cut it like at the 4 there, we end up with something like 40.00 grams. Not grams, percentage. Percent. Okay. So the same concept applies to the other elements under study. Okay. So I would give an example of the next one, that's hydrogen. So put 12 of 1.009. Okay. So the value that you should get for hydrogen should be something like 6%, 6 to 7%. So 12 multiplied by 1.009 divided by 180.156 times 100, 6.7%, 6.7% or 72%. And then for the last one, which is oxygen, it will be 6 times 15.998 over the same 180. Six multiplied by 15.998 divided by 180.156. That's giving me something like 53. How is it 53? 53.28% of oxygen. So that's it for this question 6. Simple and straightforward. Question 7. The law of conservation of mass must be considered during stoichiometry calculations. How is the law of conservation of mass obeyed during stoichiometry calculations? So we have to state it first of all. So in short, what it states is, this concept also comes from physics. Science is the same. So matter can never be created, or what? Nor destroyed. It was all created by God. We can't destroy it. We can't create anymore. Whatever was created is still there. So matter can never be created nor destroyed. So in stoichiometry, how do we apply this concept? Mass of each element present, so mass of each element present as a reactant should be maintained even on the product side. So mass of each element present as a reactant in a chemical reaction, this is its application in stoichiometry, should be equal or the same on the, or I would rather say after the reaction, or as a product if you want. Simple and straightforward, right? So if you've not yet checked out our Patreon page or our site, the link is in the description below to help you learn stoichiometry at a step. All right, so you will not regret if you try to sign up on our site. Remember, atomic structure is also where chemical bonding, all the topics that you need in chemistry, and of course even mathematics, biology, and the other courses are also there, physics. Question 8, silver has 46 known isotopes. Now the ones that exist naturally are just two, 107, 109. Given the following data, calculate the atomic mass of silver. So the relative atomic mass of any given element, the way I usually approach this is on the periodic table. If you're going to check on the periodic table, you're going to find that there's only one value for the molar mass of silver, because you can't put all the isotopes there. That periodic table of elements would just be too huge to even actually put on paper, on paper, to become a book. So to avoid that, scientists came up with the idea of relative atomic mass, where you come up with a value to present the elements. In short, you're coming up with kind of something that you approach as an average. Okay? So let's use the 2 to determine the relative atomic mass of silver. So the formula is the abundance multiplied by the mass. For one isotope, again you had another one, so the formula continues like that. In this case we only have two, so for the very first one, the abundance is 51.84% multiplied by 106.90509 plus, so this is the first part. The second part, the abundance is 48.16% multiplied by 108.90476. Grab your calculator there. I have mine here. 51.84 divided by 100 multiplied by 106.90509 plus 48.16, that's just going to be 0.4816 multiplied by 108.90476. The value I'm getting is 107.868 grams per mole. How many significant figures are we taking note of? We had 4 as the least number of significant figures, so we'd end up with 107 point, we'd even end up at 9. That's still okay, grams per mole. So this is where question 8 ends. Okay, let's continue and look at the other questions from question 9. Alright, so we're on question 9 now. So our site is learn.transcendentlinstitute.net. So on our site you can see the courses available. So specifically our focus is chemistry, right? So you can learn stoichiometry like I've been mentioning from scratch, from the introduction to the more advanced concept. You look at the moles, limiting reagent with questions there. combination analysis, acid-base titration. Practice questions are also here. You can look at balancing equations, redox reactions in acidic media. Okay, so these are just one of a few questions. You can also look at some tutorial sheets that are there. Okay, so there are a lot of other topics, as you can see, ranging from atomic structure, bonding, electrochemistry, all the way up to organic chemistry. Tutorial sheet solutions are available in video form, including the documents. So you can also open the documents. I don't just have enough time to show you. You can open the documents and access the solutions in PDF form. So this applies to all the other courses. So to register, you can get in touch with us. Use the link in the description. Get in contact with us. We'll provide more information how to go about it. For international students, visit our Patreon page. The link is in the description as well. You can also get to be in touch with us from there. Alright, so let's now continue from question 9. Consider the reaction ammonia reacting with copper oxide, and then these are the products. The focus of the question is to determine the limiting reagent and the mass of nitrogen formed. So to explain the concept of limiting reagent, what does it mean when I'm trying to determine the limiting reagent? So the limiting reagent is a reactant that finishes faster in a chemical reaction. So this, I think an example that I would give you that would make sense is think of dilution, right? Or think of dilution. Think of dilution, or instead of thinking of dilution, you can think of combustion. So for example, when you're burning something, okay, you know that combustion requires what? Combustion requires, let's say we're burning CHO. Combustion requires oxygen. Now let's assume that 10 grams of this unknown substance requires about 1.5 grams of oxygen for it to burn. This is the ratio in which they need each other. Now, as you perform a reaction, in a reaction maybe you have got 20 grams of that substance, okay? And then for oxygen, you have 2.5 grams. Which one would finish faster? So using the ratio that you know in which they react, you'd predict that if 10 grams requires 1.5 grams of oxygen, 20 grams requires how much? It's supposed to be twice as well. So it would require 3 grams. So it implies oxygen we have is not enough to burn that. So it will finish faster, thus limiting how much of this substance is burnt. This is what the concept of limiting reagent comes from. So now in this case, 2NH3 plus 3 copper 2 oxide. For now, forget about the products. Let's look at the reactants. The information we're given is for NH3 it was 18.1 grams. For copper 2 oxide it was 90.4 grams. So we can quickly determine the number of moles. Why? Because the equation, or the balanced chemical equation, has given us the mole ratios, so we can deal with moles. We can see this is in the ratio of 2 to 3. In the ratio of 2 to 3. So we can try now to find the number of moles of the two. Yeah. So the 18.1 grams we have divided by the relative molecular mass of NH3. Of course, ignore the coefficient when you're finding the molar mass. So you know nitrogen is about 14 and then hydrogen is about 1. So approximate value you should get should be 17 point something. In my case it's 17.031 grams per mole. For copper oxide, ignore the 3 as well. Check your periodic table for the molar mass of copper and then add to the molar mass of oxygen, which is well known. So if you add the two, approximate value I'm having here is 79.545 grams per mole. So let's find the number of moles now. So for the first one, the value is approximately 1.06 moles. For copper 2 oxide, the value is approximately 1.136 moles. So this is what is available, and take note, these are the number of moles available. Now let's try to use the ratios that we have in the equation. So in the equation we know that the ratios are 2 to 3. So first, to determine how much is required by 1, we can get any of the two. I would go for the very first one, 1.06 moles. I will take an assumption as though I don't know how many moles of copper 2 oxide were available, so that I determine how many moles are required by the moles present of ammonia. So cross and multiply there using the ratios. You end up with a 2y being equal to 3 times 1.06. So divide by 2. The y value 3 times 1.06 divide by 2, 1.59 moles. Now we have to understand this value that we found, the 1.59 moles. What is it? The 1.59 moles we found, those are the number of moles that would react exactly with this number of moles. Now if we check this value that is required, we compare against what was available. What is the comparison? So what is required is more, and what is available is less, implying that the copper 2 oxide is not enough, it is less. Okay, so if the opposite was true, if this value was less, it would imply it was going to be more, meaning that it was going to be in excess. So I'm sure you get the idea there. So from our calculations, or from our assumption, we've ended up finding that copper 2 oxide wasn't enough for this number of moles of ammonia. So copper was what? Was limiting. Others have got other ways of showing it, but this is the way that I prefer showing it. Okay? So if copper 2 oxide was limiting, then its number of moles is what we are going to be using in our calculations, because it's the one that's going to be limiting what? The product. So we'll use its value. So the value was 1.136 moles. These are the moles of copper oxide. So it will be useful in our calculations. Now, the question is saying we have to find the mass of nitrogen formed. So nitrogen is what we are interested in on the product side. So they are in the ratio of 3 to 1. 3 to 1, copper oxide and the nitrogen. Now we have 1.136 moles of a limiting reagent. We don't know the number of moles of nitrogen. Cross and multiply. 3x becomes 1.136, so divide by 3. 1.136 divided by 3, right? The number of moles I'm getting for nitrogen is 0.37866. These are the number of moles of nitrogen. To find the mass, we've got the number of moles. We can find the molar mass of our nitrogen easily. Okay? So we know it's 14.01 times the 2, which is a subscript. So 2 times 14.01, that's like 28.02 grams per mole. To find the mass, look at the units, grams per mole, moles. So you can just multiply the two values. 28.02 grams per mole multiplied by the number of moles. What is that showing us? Showing us the moles will cancel out, so you just remain with grams. So 0.37866 multiplied by 28.02. My calculator tells me the value is 10.61. I'm going to take it to 3 significant figures. Since I'm having 3 as a least number of significant figures, it will be 10.6 grams of nitrogen were formed in respect to our limiting reagent. We are on question 10 now. Question 10. 4 medical students were asked to conduct an analysis for glucose in a patient's blood and obtained the following results. Student A obtained the values as we can see, student B, student C, and D. If a true value is that which is the most accurate, the most precise, which student had the best combination of accuracy and precision? We have to understand the meaning of the two values. Accuracy is in comparison to the closeness of a value to the true value. Compare the values that somebody got to the true value. How close they are is accuracy. Precision is more concerned with the values being close to each other. So if I'm going to take measurements of 10.6, 10.5, 10.4, I could say the measurements were precise. They are close to each other. But if I'm going to get, or if I'm going to compare these values to the true value, as you can see, they are very far from each other. Despite them being precise, the values are not accurate. I think that's the difference that you should get. Now let's try to compare the values we have now. Which student is the most accurate student? Or even before, yeah, let's look at the values. Which one was more closer to the 59.8? 59.8. Look at the first one. The difference here is about 0.2 on the 60. The difference is almost about 0. Not 0.2 here. Yeah, 0.2. About 0.2 less. That is about 0.2 more. That one is about 0.1 more. If you check this one, 59.1, there the difference is about 0.7. 60.4, that's like 0.6 more. Of course, it has already lost in comparison to the first one. Check the third one, 59.5, that's about 0.3 difference. 60.1 is about 0.3 difference. 59.3 is about 0.5, so that has already lost as well. Then the last one, 59. That's 0.1 closer to the value. This is 0.2 more. This is 0.1. So these values, you can see that they are the ones that are more closer. So the most accurate one is D, followed by A, if my estimations are right. And then, so most accurate. Which student is the most precise? So which one is having values closer to themselves? 59.6 to 60.0, that's a difference of 0.4. And this to that, that's a difference of 0.1. This is 0.4. Check the next one. 59.1 and 60.4. That's a difference. That difference is big. This one, no. 59.5, 60.1, 59.3. The difference is big compared to the first one. And then D, 59.7, that's the difference of 0.3. And then this is a difference of 0.1. So in fact, you go around. Now 59.7 and 59.9, that's a difference of 0.2. 59.6 and 59.9, that's a difference of 0.3. So which student is the most precise? Which one is having values more closer to themselves? 59.7 and 59.9. The difference here is 0.2, not 0.4. 0.2. So in this regard, student D, the values are also still more. They look closer to themselves. They look closer. 59.7, that's a difference of 0.3 to 60. That's a difference of 0.1. Check the first one. Difference here is about 0.4. Difference here is about 0.1. Difference here is about... In short, you can go on and even just find the average. Okay? But I would assume D is the most precise. And then which student has got the best combination? Since the values which were closer to which were accurate, D again precise D. If I'm right, then D remains a student if it was more precise, right? So I don't know. So D has got the best combination. Now for 1 most accurate, you can go back again and compare all the values to 59.8. So that one again, that's the difference of 0.2. That one is a difference of 0.2 again. Then that one, that's a difference of 0.1. So 0.2, 0.2, 0.1. Then this one 0.1, this one 0.2, this one 0.1. So for me, I'm convinced D remains the best. Okay, you can verify with your trials. So our site is lane.transcendentdinstitute.net. So on our site you can see the courses available. So specifically our focus is chemistry, right? So you can learn stoichiometry like I've been mentioning from scratch, from the introduction to the more advanced concept. You look at the moles, limiting reagent with questions there, combination analysis, acid-base titration. Practice questions are also here. You can look at balancing equations, redox reactions in acidic media. Okay, so these are just one of a few questions. You can also look at some tutorial sheets that are there. Okay, so there are a lot of other topics, as you can see, ranging from atomic structure, bonding, electrochemistry, all the way up to organic chemistry. Tutorial sheet solutions are available in video form, including the documents. So you can also open the documents. I don't just have enough time to show you. You can open the documents and access the solutions in PDF form. So this applies to all the other courses. So to register, you can get in touch with us. Use the link in the description. Get in contact with us. We'll provide more information how to go about it. For international students, visit our Patreon page. The link is in the description as well. You can also get to be in touch. Question 11 is asking us to convert 1 kilometers to a nanometer. So this is going to be very simple. 1 kilometer, the kilo stands for 1,000, so it's 1 times 10 to the power 3 meters. That's a kilometer. So in short, this is 1,000 meters. Now a nanometer, when you say 1 nanometer, it means 1 times 10 to the power negative 9 meters. Okay, so when you have a kilometer, we've taken it to 1,000 meters. So if you're going to express this in terms of 1 meter, or if you're going to make 1 meter to be the subject, you end up with something like, you would have to divide by 10 to the power negative 9 both sides. You end up with something like 1 meter being equal to, in short, if you're trying to swap them, you just change the signs. So 1 meter will become 1 times 10 to now a positive power 9 nanometers. Okay, so if you're going to have 1,000 meters, which is a kilometer, you will just end up obtaining a value of 1,000 times 10 to the power 9. That would end up giving us 1 times 10 to the power 12 nanometers. Okay, so 1 with 12 zeros is a kilometer to nanometers. So you are supposed to be conversant with the prefixes. Understand that micro, if we say micrometers, it means 10 to the power negative 6 meters. Okay, look at the pico and the other things. Question 12. Here we are trying to write the UPAC names or formula for the compounds. Now for the first one, you can see the formula has been given, so they want us to give it a name. What is inside the brackets there is nitrate. What's outside is calcium. So together we form calcium nitrate. If I gave you calcium nitrate and they asked for a formula, calcium is from group 2, Nitrate is NO3 with a subscript of a negative. So if you swap them, it becomes calcium nitrate gains subscript of a 2. And then sodium sulfide. Sodium and sulfide. Okay, sulfur comes with subscript of a 2 minus. So it becomes sodium is from group 1, so sodium sulfide. Question 13. Determining the empirical formula for the compound with the following percentage compositions. So the concept is very simple and straightforward. Take the percentages to be the masses. So we have carbon, hydrogen, and oxygen. Carbon, we have 40%. So 40% divided by 100, that's going to be 0.40, right? For the 6.7, divide by 100, it will be 0.067. For the oxygen, it will be 0.533. So what's our masses? Okay. Divide by the molar mass. This is 12.01. This is 1.009. This is 15.998. So in short, we're trying to find the number of moles. Okay. So let's go on and do that. 0.4 divided by 12.01. So 0.0333. So it's okay without even dividing by 100. If you want, you can just take them as 46.753.3. That's still fine. So let me take the values to at least 4 significant figures, or 5 significant figures. And then the next one, 0.067 divided by 1.009, 0.06640, 0.533 divided by 15.998, 0.0333, and then that's like 1.6. So if you compare them, if we're going to go for the first 3 significant figures, these two are just like the same, and then the other one is like 0. What value is that? 0.66. all right, 0.0664. So these are the number of moles, and what happens when you find the number of moles, divide by the least or the smallest value. In this case, it's 0.03305. So of course, if I rounded off, this would be to 6. This would be 6. So 0.03306 of the sum. This would be 7 if I round it off. So of course the first one will give us a 1. The second one, 0.06640 divided by 0.03306. That's something like 1.99, which is just like a 2. Then the other one, 0.03317 divided by 0.03306, 1.000, so which is just a 1. So the formula becomes CH2O subscript of a 1. Okay. Alright, question 14 is related to the question we are from solving previously to do with limiting reagent. So 80 grams of iodide 5 oxide, which is that, reacts with 28 grams of carbon monoxide as the reaction entails. What are we saying now? Determine the mass. The mass of what? Determine the mass of iodide which could be produced. Okay, so that's our concern. So even if the question doesn't state, you can only predict how much would be produced if you determine the limiting reagent. So that's a very important concept you need to know. So I have 80 grams of this, and then we have 28 grams of carbon monoxide. So I have to first of all divide by their molar masses and then determine the limiting reagent. Okay, so what is the molar mass of, so use your predictable iodide, and then of course oxygen. Iodide is about 126.904 times 2, and then plus oxygen, which is like 15.9994 times 5. So if we add this, should give us the molar mass of, of iodide of 5, which is giving me something like 333.80594 grams per mole. If you go for the, so you can just divide. Then if you go for a part for the carbon monoxide, so carbon, we know it's 12.01, and it's only 1 plus 15.9994 for our oxygen. Grabbing my calculator there, 12.01 plus 15.994 is 28. So that should be able to give us now the number of moles. Grab your calculator and then start dividing. So of 8 divided by 333.80594, that's 0.23966. So that's the number of moles. For carbon monoxide, 28 divided by 28.0094, it's like a 1. So 0.99966. We can use any of the two. I'll use the first one. So the mole ratios were in the ratio of 1 to 5. So I'll assume I don't know that value so that I can see the value to compare with. So if I cross and multiply and then put a y there, we end up 5 multiplying by that value. So 5 multiplied by 0.23966, something like 1.1983, which is of course definitely higher than what was available. So therefore carbon monoxide in this case was limiting, right? Carbon monoxide was limiting. So in such a case, we ignore all other calculations and use the number of moles of carbon monoxide, since it was less than the amount that was required. So now if you compare it to the iodide, you notice that they're in the ratio of 5 to 1. They're in the ratio of 5 to 1. So we have to find the number of moles of iodide. So 5 to 1. Can put y there to find the number of moles of our iodide. So if you cross and multiply, y is going to be 1 times that divided by 5. So 0.99966 divided by 5. The number of moles, we have 0.199932 moles of iodide. Now check your periodic table. for the molar mass of iodine. I think the value is something like 109 something, right? So the molar mass of the mass can be given as a product of the molar mass, okay, which was something like 109, hopefully that's accurate, multiplied by 0.19932 moles. Okay. So we should have issues with students shouting at you. So the value of the molar mass of this is actually 126.9 times 2. Let me use the actual value. 126.9 times 2. That's like 253.8 grams per mole. And then if you multiply that now, 0.112332. So the value is the moles would actually cancel out. So the value I'm getting is 50.74 grams. If we can go by the least number of significant figures, we had 3. So 50.7 would be okay. Question 15 is dealing with the issue of assigning the oxidation numbers. Okay. So look at question 15. For the first part, we have carbon in HCO3 minus. And then hydrogen is +1. Carbon is what we're trying to find. We'll say X. Oxygen is -2, equal to the net charge, which is -1, to find the value of X. So we have 1 minus 6 plus X is equal to -1. We have -5 plus X is equal to -1. Then X is -1 plus 5. That would be a 4. So +4. Alright, so for 2, Fe in ion to sulfide or sulfate, so some of these, if you want to be a bit faster and smart about it, is when you look at this guy in the brackets, SO4 has got a charge of a 2 minus. We can actually tell from that subscript there. That's how the formula came about, right? And actually, without even wasting time, I can also tell that the oxidation number of this from the question is just actually 3, because they exchanged, they swapped. This became 2, that became 3. So without even wasting time to perform any calculations, we can see that the oxidation number of ion in this case was a +3. Yeah. And then for the last one, that is oxygen in sodium, I don't know, dioxide or something. Sodium is group 1, so 2 times +1, and then 2 times our oxygen X. The net charge here is a 0, so 2 plus 2x is equal to 0. So you end up with a 2 divided by a -2 divided by a 2, which would give us a -1. So this is where we end for this tutorial sheet. I just hope that you've learned 1 or 2 things, right? So to access more videos, make sure you use the link in the description, either on our Patreon page, our site, for you to subscribe to courses and find access to all the videos in all the courses at a very affordable fee. Thank you very much once more for watching. Give us a comment about the video if you liked it. So our site is lane.transcendentlinstitute.net. On our site you can see the courses available. So specifically our focus is chemistry, right? So You can learn stoichiometry like I've been mentioning from scratch, from the introduction to the more advanced concept. You look at the Mohs limiting reagent with questions there, combination analysis, acid-base titration. Practice questions are also here. You can look at balancing equations, redox reactions in acidic media. Okay, so these are just one of a few questions. You can also look at some tutorial sheets that are there. Okay, so there are a lot of other topics, as you can see, ranging from atomic structure, bonding, electrochemistry, all the way up to organic chemistry. Tutorial sheet solutions are available in video form, including the documents. So you can also open the documents. I don't just have enough time to show you. You can open the documents and access the solutions in PDF form. So this applies to all the other courses. So to register, you can get in touch with us. Use the link in the description. Get in contact with us. We'll provide more information how to go about it. For international students, visit our Patreon page. The link is in the description as well. You can also get to be in touch.